This begins our coverage of topics in Chapter 10. We'll begin by discussing some general concepts about input-output. Parallel I/O is data that is sent over a group of parallel wires. Typically, a clock is used for synchronization. This diagram shows CPU number 1 using a 16-bit data bus to send data to CPU number 2, and we're going to assume that this clock is used to send the data and that these 2 bytes are sent every rising clock edge. A measurement of how fast data is sent over a link is called bandwidth, and you compute it by taking the number of bytes divided by the amount of time that it takes to send the bytes. In this example, we're going to have 2 bytes divided by the clock period of this clock, which if we assume is 300 megahertz, is going to be 1 over 300 million. If we calculate this out, we're going to get the bandwidth of this link is going to be 600 million bytes per second. Serial I/O is where data is sent 1 bit at a time over a single wire. A clock may or may not be used for synchronization. This diagram shows CPU number 1 sending serial data to CPU number 2, and we're using a clock for synchronization. Let's assume that we're using a rising edge to send each bit as a previous example. So how fast would this clock period have to be if we wanted to achieve the same bandwidth as in the previous example of 600 million bytes per second? So first thing we have to do is convert bytes per second to bits per second. We know that there's 8 bits per 1 byte, so this is actually 4,800 million bits per second. So this is our bandwidth. We know that bandwidth is equal to how many bits is sent in how much time. So we have 1 bit set each clock period. If we take 1 over the clock period, this transforms the clock frequency. Now what we can do is this bit unit cancels out that bit. We're left with 1 over seconds, which is actually equal to hertz, and so our clock frequency ends up being 4,800 times 10 to the 6 hertz, which is going to be 4.8 gigahertz. A more intuitive way to get this figure is to simply note that this clock frequency here was 300 megahertz, and we're sending 16 bits of data each clock period. If we now want to make this 1 bit of data each clock period, but yet still achieve the same bandwidth, then we simply have to say, well, we got to speed this clock up 16 times. So 300 times 16 would be 4,800 megahertz, which is going to equal to 4.8 gigahertz. So let's talk about some pros and cons of parallel versus serial I/O. First of all, in terms of bandwidth, parallel I/O is the king if you just want absolute maximum bandwidth. You can increase the bandwidth by either making the data channel wider or increasing the clock frequency. You can arbitrarily achieve a bandwidth by simply adding more parallel wires. The problem is these parallel wires are expensive. Wires cost money. Also, if you put these wires in a cable, the cable is very bulky, and parallel wires right next to each other can cause crosstalk, which would mean data corruption. Crosstalk is where a transition on one line can affect the data on a neighboring line. So with serial, it's cheap in terms of the number of wires. Very few wires, cables, very flexible, easier to pack a lot of serial cables in a small area. Typically, this is good for a long distance interconnect, and by long distance we mean inches to feet. Another good rule of thumb is that basically if an interconnect runs off the board, off a computer board, typically that's going to be serial interconnect. It turns out that integrated circuit technology has steadily improved over the years, and now it turns out that we have new fast serial I/O standards such as USB 3, FireWire, serial ATA that have replaced older parallel I/O standards. In fact, it's standard now that where we used to have parallel I/O to our disk drives inside personal computers, we now use serial connection. Because of this faster integrated circuit technology, what used to only be achievable via parallel I/O is now achievable by serial I/O. And if you ever have a choice of using either parallel or serial I/O, you will always go with serial I/O simply because it's going to be much cheaper. However, the fastest serial link will typically have lower bandwidth than the fastest parallel link, so it all depends on what type of bandwidth you need. Let's introduce some definitions for communication channels. A simplex communication channel allows communication in one direction only. Here, CPU 1 can only send data to CPU 2. Half-duplex communication allows communication in either direction, but only one direction at a time. So here CPU 1 can be sending data to CPU 2, or CPU 2 can be sending data to CPU 1, but they cannot be sending data to each other at the same time. Finally, a full duplex, or sometimes simply duplex, communication channel is where communications in both directions at the same time can be achieved. So a full duplex communication channel allows CPU 1 to be sending data to CPU 2, while CPU 2 is also sending data to CPU 1. So we will use wires and voltage signaling to implement communication channels in this class. Wires with voltage signaling are either simplex, which means that communication occurs in only one direction at a time, such as in this diagram, or they are half-duplex, in which we use a tri-state buffer here and a tri-state buffer here in order to achieve bidirectional communication, but it's half-duplex. If this buffer is enabled, then we're going to be sending data in this direction. If this buffer is enabled, then we're going to be sending data in this direction, and they both cannot be enabled at the same time or else we'd have a clash. If we were going to implement a duplex communication channel, that is communication in both directions simultaneously, we would need to have two simplex wires. Synchronous serial I/O means that somehow when data is sent from a CPU 1 to CPU 2, that also a clock signal is sent. Now this can be done in two ways. The easiest way is simply to send the clock as a separate wire. Another way you can do it is essentially send it virtually, in which somehow this data stream is encoded so that you could extract the clock from the data stream, or alternatively you can use an integrated circuit block called a phase-like loop, and changes in the data stream to synchronize an internal clock to this data stream. If PLL synchronization is used, then there are some constraints on this data stream. The data line must be guaranteed to have a minimum number of state transitions, 0 to 1 or 1 to 0, within a particular time interval. This is called a guaranteed transition density. Synchronous serial I/O standards can achieve very high speeds, and it turns out that all new high-speed serial standards are synchronous. The popular serial standard USB, which stands for Universal Serial Bus, uses this particular method for synchronization. Asynchronous serial I/O does not send the clock with the data either by a separate line or by extracting a clock signal from the data. This means that the two CPUs that are exchanging data must have clock frequencies that match within a certain tolerance. They can be out of phase. It turns out that asynchronous serial I/O is used in older standards, is easy to implement, but it is slower than synchronous serial standards. We're going to begin our discussion of serial I/O standards by looking at a very common asynchronous serial interface standard that in its basic form only requires 3 wires to implement a duplex communication channel. A version of this interface standard is known as RS-232. It turns out there are more wires defined in this standard, and it uses different voltage levels. We're only going to use 3 wires, and our voltage levels are going to be 0 volts to whatever VDD the PIC24 is running at. This diagram shows CPU connected via the serial I/O standard. There's a transmit line that's going to be connected to the receive line of CPU 2. There's a receive line here on CPU 1 that's connected to the transmit line CPU 2. So this data on this line flows from CPU 1 to CPU 2. The data here flows from transmit to receive, so from CPU 2 to CPU 1. So each of these wires are simplex, but this is a duplex communication channel. There's a ground wire that needs to be connected between each CPU. They have to have a common ground because we're using voltage signaling, and so we have to know what the 0 voltage reference level is. This slide shows the serial data format for this asynchronous standard. We're going to start with this one right here because it's the one that we're going to be using in our examples in the lab. The line, when it's not sending any data, is in what's called a mark condition, which is a logic 1 or a high. In order to start transmission, it's going to undergo a high to low transition, and this first time period here is going to be a serial bit known as the start bit. This is how a receiving CPU detects that transmission is started. After that, data is sent serially, with each time being 1 bit, with data being sent least significant bit to most significant bit. This particular format is sending 8 data bits and then 1 stop bit. Well, what's 1 stop bit? 1 stop bit is the minimum amount of time that the line must be high before another transmission can start. You can have, some of these formats can have 2 stop bits, which means that the data line will have to be high for 2 bit times before it could actually begin another transmission. In this particular format here, the 8th data bit is only sending 7 data bits. The 8th data bit is called a parity bit, which we'll discuss on the next slide. A parity bit is an extra bit that's added to a data frame to detect a single bit error. What is a single bit error? A single bit error means that if you send a 0 and it receives a 1, that's an error. Or if you send a 1 and it's received as a 0, then that's an error. This parity bit is not guaranteed to detect multi-bit errors. It is guaranteed to detect a single bit error. So what does odd parity mean versus even parity? It turns out the parity bit can either be the odd flavor or the even flavor. Odd parity means that what I'm going to do is I'm going to add the parity bit such that the total number of bits in the data is going to be an odd number of ones. So for example, if I'm trying to send a 7-bit value 56, which is going to be this 7 bits, then I have 1, 2, 3, 4 ones in the 7-bit data. My parity bit that I'm going to add to this is going to be a 1. That would make the total number of 1 bits odd. If I was going to send an even parity bit, then because I already have an even number of 1s, the parity bit value would be 0. How does a parity bit detect a single bit error? Well, let's assume we're sending this data here and we get a single bit error, and let's just assume that this bit right here was received as a 1 instead of as a 0. The receiver is counting the number of 1 bits it received for this frame, so it counts as 1, 2, 3, 4, 5, 6. It counts 6 1 bits. It knows that it's supposed to be receiving odd parity, that it should have received an odd number of 1s. So because it received an even number of 1s, it's detecting an error. What if we have a multi-bit error? So let's say that this bit here, 0, got changed from a 0 to a 1. But let's say that this 1 bit here also got changed, and it got changed from a 1 to a 0. Now the receiver is counting 1 bits as it receives it, and it counts 1, 2, 3, 4, 5. It receives an odd number of 1 bits. It has odd parity, so it doesn't know. It thinks that it received the right value when in fact it is a value that's an error. So parity is not guaranteed to detect multi-bit errors, but it is guaranteed to detect a single bit error. So let's take a look at examples. Let's take a look at this one first, AD, which is going to be, this today format is going to be 8 data bits plus 1 stop bit. So this AD, here's the A, here's the D. So let's send this data. Here's our start bit. It always goes from high to low. Our least significant bit here is this guy right there. That's that least significant bit. This next 0 is that guy. This next 1 is that one. This next 1 is this one. This next 0 is here. This next 1 is this guy. This next 0 is this bit right here, and this last 1 is this. Now, after we send this last 1, the line still has to remain at a 1 condition for 1 stop bit time before it can actually start another transmission. Generally, serial data is not sent as fast as you can. Generally, these lines can have large idle times between characters. Both the receivers and the transmitters are going to have clocks that they're going to use to clock the data out and clock the data in. They're typically either going to use 4 clock periods to sample the clock, or 16 clocks for each bit time. This diagram right here shows the receiver using a 16x clock, that is 16 clocks to sample a bit. Both the receiver and the transmitter must agree on the data rate of this channel. That is, they have to agree on what this clock frequency is going to be before they start sending. So what's going to happen is that the receiver is going to be watching this line, and when this line transitions from high to low, it knows that I'm beginning to send data. So it's going to start counting clocks, and it's going to count 8 clocks. And when it gets to the 8th clock, which is going to be right here, it's going to say, oh, what I need to do is I need to look at this line and see if it's a 0 or a 1. Of course, the very first bit time, you're guaranteed that it's going to be a 0 because it's a start bit, but after that, it could either be a 0 or a 1. So once it samples this input, what it's then going to do is it's going to count 16 clocks, which is going to put it at the middle of the next period, and it's going to sample the line again, and it keeps doing that until it's clocked in the expected number of bits. So why do I use 16 clocks to sample 1 bit time? The answer is easy. The receiver and transmitter clocks are not perfectly matched. They may have some slight mismatches in terms of frequency. They are also out of phase. What out of phase means that their clock edges do not line up. Because they start up at different times and there's no way to synchronize, that is, align their clock edges. So sampling 16 times gives me error tolerance. It means that we're looking at this bit time about in the middle of the bit time. Now, this receiver-transmitter mismatch builds up over time. The error due to this mismatch is cumulatively adds every new bit that I clock in. So what that means is I don't want to have a frame consisting of a whole lot of bits. The number of bits that we're going to use in our frames are either going to be limited to 10 bits or 11 bits, depending upon how many stop bits we have. For 10 bits, what we have is we have one start bit, 8 data bits, plus one stop bit. For 11 bits in a frame, we have one start bit, 8 data bits, and 2 stop bits. So if we assume a 10-bit frame, then our maximum mismatch between our receive transmit clocks, because we have 50% error tolerance here, half a bit time, then a maximum mismatch we could have would be 5% mismatch between transmitter and receiver. In practice, though, we really can't get 5% mismatch. There's also some error due to the rise and fall time of signals, and in practice, this maximum mismatch is actually closer to between 3% to 4%. Let's talk about some terms relating to how fast data is sent over this asynchronous serial link. Common usage is to refer to the rate at which bits are sent over the serial link as baud rate. Baud rate is a technical term which says the rate at which signaling events are sent. A signaling event is not necessarily equal to 1 bit. We'll talk about that in a minute. Another term is bits per second, in which bits per second is the number of bits transferred per second. Now it turns out that if only a 1 or 0 is sent for each signaling event, then baud rate is equal to bits per second. It turns out that there are commonly defined baud rates for asynchronous serial links. They have to be predetermined because both the transmitter and receiver have to agree on them. Typical baud rates are 300, 600, 1200, and so forth, typically doubling each time, but not always. We're going to use in our class a baud rate of 57600, and what this means is that because we're only sending a 1 or 0 for each signaling event, it turns out that 1 over the baud rate, or 1 over, is actually equal to 1 bit time. So the amount of time it takes to send one of these bits is going to be equal to 1 over the baud rate for how we're using this serial link. So in this class, we're going to use baud rate and bits per second interchangeably when referring to this asynchronous serial protocol, because we'll only be sending a 1 or 0 for each signaling event. When would baud rate not be equal to bits per second? Well, you would have to have a signaling protocol that would transfer multiple bits per signaling event. For example, you could use 4 different voltage levels and send 2 bits per signaling event. For example, I could use a minus 15 volts to represent the 2 bits 0, 0, a minus 5 to represent 0, 1, a plus 5 to represent 1, 0, and a plus 15 to represent 1, 1. In this case, the bit rate would be double the baud rate. You can also compute an effective data rate, which is the rate at which data is transferred minus the overhead bits. Well, what are overhead bits? Overhead bits are things like the start bit, stop bit, parity bit. These do not contribute to the data. They are simply used to synchronize this data transfer and also do error detection. So in order to compute an effective data rate, what you would do is you would take the total time for the frame, so this amount of time here, and you would say that time divided into your total number of data bits, which in this case would be 7, and you're going to get a rate that's going to be lower than the bits per second because I have the extra time dedicated to sending the overhead bits. Let's look at some sample calculations involving this protocol. Problem 1 says, what is the bit time in microseconds for a baud rate of 57600? We know that bit time is equal to 1 divided by the baud rate. So 1 divided by 57600 is equal to 1.736 times 10 to the minus 5 seconds. To convert to microseconds, we multiply by 10 to the 6 microseconds per second. We end up getting 17.36 microseconds. Problem 2 says, how long does it take to send 20 bytes of data at a baud rate of 19200, assuming a data format of 1 start plus 8 data plus 1 stop? Give the answer in milliseconds. Our total bits is going to be equal to 20 bytes times 8 data bits plus 1 start bit plus 1 stop bit is going to equal to 200 total bits. So our total time will be the total number of bits times 1 bit time, or 200 times 1 over 19200 is going to equal to 0.01042 seconds. To convert to milliseconds, we multiply by 1000 milliseconds per second, and we get an answer of 10.42 milliseconds. So let's take a look at this serial data protocol in a logic analyzer. Here, a logic analyzer is going to be monitoring the receive and transmit lines of the PIC24, and I'm using the PIC24 bully bootloader and echo.c program to send it serial data. Here I sent an A and I got echoed as a B. We can see that captured. I'm going to go ahead and send something different here. So let me go ahead and get this guy set up to capture, so I'll do that. Now I'm going to go ahead and have it looking for a trigger. At this point I'm going to go ahead and let's send a C this time, so I'm going to do that. So I just sent it a C. I'm going to go ahead and zoom back out so we can see this whole thing. And now what we've done is we see that we received the C and received the D. This first bit right here is the start bit. Let's look at this in binary so you can see the data pattern. So I'm going to go here to settings and change this interpreter to be a binary view. So I'm going to configure this to take a look at it in binary. So let's do that. So now that we see that this first bit is the start bit, the next 2 bits are 1, so that's these 2 1s. Then we have a string of 3 zeros, then 2 1s, and finally we have a 0 here, which is the very last bit. That's the most significant bit there, and then we have the stop bit and a long period of idle time. Let's go ahead and measure 1 bit time. So what I'm going to do is I'm going to zoom in on this start bit here. I'm going to put down some cursors to measure the start bit time. So let's do that. Put down a vertical marker here, put down another vertical marker, and measure this 1 bit time. So 1 bit time here, it says that it's 17.3 microseconds approximately. Remember in our sample calculations that we computed at about 7.3 microseconds. So we're pretty much dead on in terms of this bit time calculation.